All right, good afternoon, everybody. My name is Charles Neveze, and I'm the Vice President, Business Development and Commercialization with the Center for Excellence in Mining Innovation. And you know what, we're really excited today to be hosting the Young Persons Lecture Competition, the Canadian edition. And today we're gonna run from about 2 o'clock to 4:30 p.m. With me on the call is the judges, which you will see shortly, and also our first contestant. And we also have some guests with us as well to witness this competition. But before we jump into the presentations themselves, I'd like to acknowledge where we are. Currently, I am in Robinson Huron Treaty Territory, and the land in which I'm presenting from is the traditional territory of the Atikmashang Anishinabeg, which is the Sudbury, Ontario area. Here's how we're going to go through the presentations. We're going to start off by having an introduction to the judges. We will acknowledge our sponsor, who's sponsoring the Canadian edition, the prize for the Canadian edition, and we'll also go into the actual presentations themselves for the students. About close to 4 o'clock, the judges will go offline, and they'll then come back online to make an announcement of the winner for this competition. I'd like to now introduce to you the judges themselves. And I want to start off by bringing Martin Jones to speak. Martin, I'm going to spotlight you here, and I'm going to ask you to introduce yourself. Please go ahead, Martin.
Yeah, thank you, Charles, and good afternoon, everybody. So my name is Martin Jones. Day job, I work at Rolls-Royce. I'm based in the UK. I'm actually the team leader for the services research and technology team. So developing new services, inspections, principally for gas jet turbine engines. I'm also the global process owner for power technologies in Rolls-Royce. And then I also wear another hat, so I'm the chair of the members board as well at the Institute of Materials, Minerals and Mining. So that's me.
Okay, thank you very much, Martin. And I just want to let everyone know as well that Martin is the chair of our judging committee. Thank you for that. Next, I want to just bring up our next judge, who's Edward Thomas. Edward, could you please introduce yourself? And I'm going to spotlight you as well. Go ahead.
Hi, how are you doing? Edward Thomas. I work in astroparticle physics research. Famously, we conduct a vast majority of our research in Canada at about 2 kilometers underground in the Creighton mine. So we are familiar with the industry. My background is in business journalism and chemical engineering. I've spent about 20 years in innovation and research development, helping everything from startups to large research enterprises.
Thank you very much for that, Edward. Okay. Let's remove you from the spotlight here. Okay. So moving on with our agenda, I want to take a moment to thank our sponsor for the student award. So the winner of the Canadian session is going to receive this award from BRIM, and BRIM is the Bradshaw Research Initiative for Minerals and Mining based out of British Columbia. And BRIM also has a really awesome relationship with MICA, which is the logo you're seeing here. They're one of the main partners for this network called MICA. But they do have a short course, an online course, which will introduce the students to the mining industry in a really innovative way. And again, this is a present that will be given to the winner of the student competition. So this is the agenda for the student presentations. We are now on our second student here, Yusuf, who's going to present next on refrigeration from engine energy for fuel efficiency right systems. So Yusuf, if you could just take over the screen, please go ahead and do your presentation. And when you're done your presentation, Yusuf, what we'll do is we will have about a question each from each of the judges, and those questions will be directed towards your presentation to maybe get some clarification on what it is that you've shared with us. Yusuf, please go ahead.
Still, I can't share my screen for some reason.
Okay, are you good now? Go ahead.
Can you see my screen?
Yes.
Yes.
Okay, great. Hello, judges. I guess this is one of the times that I need to be happy for being judged. And it's a nice job that you have. You're being appreciated for judging others. So feel free to judge me as much as you want. What is my project? It's called Reefers. It's refrigeration from engine energy for fuel efficiency rise system. I know some people say that reefer means marijuana, but also reefer means that the long haul trucks for refrigerated trailers. I don't know if there's a relationship between truck drivers and truck driving and marijuana. That's not the topic of today. But yeah, let's have some facts about trucks and reefers. So in 1940, the first mechanical refrigeration unit for trucks was manufactured in the US. 90% of the food Americans eat every day is shipped by reefers, refrigerated trucks. Regular reefer drives more than 1 million miles, and that's a very good number, an important one for future slides. We'll see why. To put that into perspective, your regular cars drives only 0.2 million miles. Reefers also maintain a temperature between 55 Fahrenheit to minus 20 Fahrenheit. And I didn't use Celsius here because the next stage will be in the UK. So they're used more into this units. Lastly, how many reefers are in the world? Only in the US, there are 500,000 reefers. So there is a big market. Here, let's talk about some needs. The world is expected to run out of fossil fuels in 60 to 100 years. And especially here in the UK, fuel prices almost doubled from 2020 to now. And in general, transportation takes around 29 or 30% of the energy demand, the global energy demand in the world. There is here a little bit kind of misconception. Some people don't know that. The electricity generation comes mostly from fossil fuel. So even if you are using electricity, it's basically coming 60% of it fossil fuel, only 20% of it is coming from renewable energies. There are, of course, the 17 goals, the Sustainable Development Goals. The United Nations put these as goals till like 2030. Till 2030. In my project targets 4 of them: affordable and clean energy, industry, innovation and infrastructure, climate action, partnerships for the goals. So now, I guess I can ask some questions here. How many of you drives?
Oh yeah.
Yeah, I drive.
Yeah, all of you. Do you like the fuel prices?
No.
Yeah, so and do you know that 65% almost of the internal combustion engines energy is wasted, is a waste energy, and most of it is heat. So basically, if there's a, let's say this cup of water, I drank only like 35% and there's 65%, I'll toss this out. It's a waste. And that's a good way to drink water during my presentation. So yeah, and one more fact, refrigerated trucks typically carry an extra diesel engine and an extra fuel tank to power their large fridges at the back. So what is the project? It's an innovative waste heat recovery system, which is going to be placed on the truck. This is the fuel tank, and this is the fridge unit. And we are going to remove here the compressor and the diesel engine from here and the fuel tank. And I'll add my system to the truck to replace these, which will use the waste heat from the internal combustion engine and power the fridge unit. So it's basically a replacement. How does it work? It's like a simple Rankine cycle system, or if you want to call it like a heat engine, or it's something similar to a steam turbine. It's basically the waste heat will go to a heat exchanger, and simply the heat exchanger will absorb the waste heat, and the fluid inside will evaporate, converts into a steam. That steam will rotate the turbine, and then here with rotation, we can generate electricity out of it. This is just to complete the loop. It's a radiator, if you want to call it a condenser, and a pump to complete the Rankine cycle loop. So that's how it works. The key features of this project, it's that it's a replacement for the existing refrigeration power unit on the reefers. So it's basically, we're not adding we're replacing. So we have plenty of space to put our system in. The weight is almost the same between the weight budget between the current system and the new system. Maintainability will be also not more, because it's a replacement of the system, and we can have some salvage cost of the previous system that we are replacing. It's aftermarket, so it's not for new productions. It's for the trucks that they are already on roads. And that's very important, because we are not competing with electrifications. We are basically facilitating electrifications. And for maybe the coming 15 years or 20 years, before these long haul trucks phase out, our system will work. This project can be applied to other vehicles as well. But as a start, and for many other reasons, we're only targeting the long haul trucks with refrigerated trailers. What are the results of the project? Less fuel needed for the truck, and that will increase the efficiency of the truck fuel consumption, and that will save money and cut CO2 emissions. The estimations of the CO2 emissions, the cut will be around 40,000 kilograms of CO2 emissions yearly per one truck. And that's based on the calculations, which that we are saving around 75 liters of diesel every day for each truck. Now, some other technologies around, or like products, which is similar in a way to our project, but different in other ways. And that's here we're making a comparison. Tesla, everyone knows Tesla. So the differences between the project that I have and Tesla, it's Tesla uses electricity, and electricity mostly comes from fossil fuels, as we explained earlier. The second thing is for new productions only, and my project is not for new productions, it's for the trucks on roads already. And the latest Tesla trucks, it's called the CEMI truck. The manufacturing of that will start in 2023, and the cost of it will be around $200,000, which is more expensive than a new regular truck, which is around $80,000 or $90,000. Now we'll move to the hybrid system. Why there is no hybrid system on these trucks, which use electricity and fossil fuel? Now there's no hybrid on long-haul trucks. That's something. And why? Because it's hard to implement for the aftermarket trucks, and it's expensive to implement on the new productions. Turbochargers basically, they make the performance of the vehicle better with when there are like high speeds. That's the simple concept of the turbochargers. So what are the differences? First, they don't save fuel. They permit more fuels to the engine block, so that's something. They cause sometimes overheating problems, and my system don't cause overheating problems. And also they reduce engine life because of some extra pressure added to the engine. Okay, and I have a team helping me. There is Aryan, fourth year mechanical engineering. He's the most passionate in my team. There is Gabriel, who has a very long experience in that field, 15 years of driving at York University, and 3 years of reefer truck driving in Canada. So, and he worked in Volkswagen in Germany, and also he had tanks industry work in Romania. He already had automotive industry diploma. He's a 60 years old man, and he has a very long experience in mechanical stuff. I have Ibrahim from marketing. I have Mamoon. He is an automotive mechanic from Centennial College here in Toronto as well. I have Khaled from Schulich School of Business, and soon to just invite another member from the law school to help me in the team. I have another circle which they can help. They're not part of my team, but they can help me whenever needed. I have Michael Bardilabin, company manager in Dana Incorporated. I have Eric Paul, he's a senior engineering manager in Dana Canada Corporation. I have a friend who is truck driver, and I already inspected his truck. He owns a long-haul truck, and he's interested to implement my system on it when it's ready. And he gave very positive feedbacks as well. Daniel Sugar, mechanical engineering graduate, and he has a long hands-on experience. And I have Professor Thomas Cooper from the Mechanical Engineering Department, York University. I had endorsements from many people on my projects. One of them is the director of our mechanical engineering department, Professor Hussam Sadiq at York University. Professor Roger Kempers, all his research about heat and heat analysis and research. And this is me with Dr. Mike Bardelabin, the Dana manager. That's in 2020. So what I have done so far, I inspected a truck, Class 8 Kenworth truck. I also designed all the parts, all the components of my system. I completed a report of 150 pages about everything regarding my my project. I proved the concept with the prototype, scaled down prototype, and that was during my capstone project in the past, like the past year. I contacted many companies as like an outreach to see their feedbacks and if they're okay with implementing it, and many other informations like Kenworth, Metro, Walmart, and so on. Soon to come, starting tomorrow, I'll start to build my complete actual size system, because the one I did is just a proof of concept, scaled down size, but now it's going to be a complete actual size system. I had like a meeting with the entrepreneurship department yesterday, and they gave me funds for that. That's why I'm starting tomorrow with the shopping list and these new design and everything. And now the business side of it. And I like that we have people from the business field, and we have people from Rolls-Royce and innovation and other places in the judges. So the business case, we in this project saves the user around 75 liters of fuel every day per truck, of course. The cost saving is going to be around $4,000 a month. The estimated payback is going to be from 7 to 10 months because the cost of the system is from 10 to 20, $10 to $20,000. Sorry, 10 to 15. My bad. Yep. And these are lastly. Here, I would like to conclude by this saying, if you have done something once, you can do it again, or you can do it even better. And that's by Ashton Eaton. He has 2 gold medals, like he's an Olympic athlete. And actually, I did a similar project in 2013. I was working in a paper factory, and they had like a lot of paper waste and cardboard waste. And they were paying money to get rid of these actually paper waste. So I was thinking, why don't we just sell it and take the money for our pockets? And then I connected with some people who are doing recycling in that field, and it worked. It worked for a year. And instead of paying $100 every 2 weeks, we were paid almost $100 every 2 weeks. So it's 200 difference. Saving 100 and getting paid 100 for that recycling. So maybe you want to call me the recycle man or something like that, but I've done this before, and I think energy sector is not a lot different from the hardware paper recycling field. So yeah, that's everything I have today, and thank you for listening.
All right, thank you very much, Yusuf, for that presentation. That was a very interesting presentation, and learned a lot about heat exchange systems there. What we're going to do now is Yusuf is moving to the question period. I'm going to invite Edward to be the first person to ask you the question. So Edward, please go ahead and ask your question.
Only one question, huh? Chemical engineering, he has many questions, but if I recall correctly from my own background, I mean, the maximal efficiency of any Rankine cycle would be about 60%. Practically, we're talking 50%. Do you have a target efficiency recovery metric that your system should be able to accomplish? And I may sneak a follow-up into that answer.
Yeah, definitely. So generally speaking, it's around like 10% of the waste heat, and that in the mechanical word, that's a high percentage. But the thing is, there are so many conversions, and even I showed the simple loop, not the very detailed technical loop that I have. So because it's a complicated loop, kinda a little bit more complicated than the Rankine cycle that I showed. But yeah, with every conversion, I lose efficiency. I lose like some waste heat, but like the final one is going to be around like no more than like 10%.
Okay. And I guess the follow-up, and it's an entirely different question, I'll just cop to it. Component selection. So, I mean, a Rankine expansion turbine is potentially a breakable system. Have you found an off-the-shelf component that will do the job for you?
Which component exactly you're asking?
Turbine in particular.
Yeah, the turbine, I have the more details in my report. We looked at some options. So far, I didn't find off-shelf, but like, so it's probably gonna be manufactured when I wanna put it in the truck. But now I might just modify some other systems at this stage, for example, like turbochargers themselves or turbo steamer or something like that, because they usually use heat. So that's the thing I'm using.
Thank you.
Okay, thank you very much, Edward, for that question. Next, I'm going to ask Martin to please ask a question or two.
Yeah, thank you, Charles. I'll try and stick to one. Although I've got a few. That's good. So I guess my main sort of thought as I was listening to you, Joseph, and some really interesting facts and figures in there, is certainly in Europe, and I'm going to assume it's the same in Canada and the US. Truck drivers often have to stop overnight, and they switch engines off, which is why they have the small diesel engine that you alluded to right at the start. So how would your system cope with truck drivers stopping and switching the engine off at night time?
Yeah, so there are many steps for that. First, the battery that we are adding, because I'm generating electricity, and the electricity will be stored in a battery in my system. The battery that I'm having, it has some percentage in idling periods, so that would be covered with the battery. And the thing is that the percentage of driving and stopping, I did some research around that. That's how I made my battery to cover this period. And usually, if they either go small distances, so they'll be running all the time, or they switch drivers. So sometimes they drive for 24 hours and they have 4 drivers, and they just switch every 6 hours. But for they don't stop for a long time during night if they're only one driver, because that's also a waste of energy for the goods at the trailer. Also, one more thing, that I'm using electrical compressor, and I have a battery. In case the system failed or it ran out of energy, it can be plugged in. But that would be electricity paying with comparison to my system, which is for free electricity, basically.
Okay, thank you. I must have missed the battery system on your schematic there.
Yeah, I didn't add that, but I said in my schematic. But I said after the turbine, I have the electrical generation, and with the electrical generation, I'll have a battery.
Okay, thank you.
Okay, thank you, Martin, for that question. My question is really going to follow up on the new information that we have now about the fact that there's a battery system attached to this. In the mining industry, right, we produce a lot of heat when we are doing things like smelting, right? And also, I know that, for example, just in the commercial market for buildings, commercial building market, the HVAC systems produce a lot of heat, right? And there's a lot of heat being lost there, a lot of this low-grade heat being lost into the atmosphere. So I know you're sort of focusing on trucking, right? But have you looked into other use cases that may be more static, maybe more static infrastructure that doesn't need to move around and go through different regulations? So I guess maybe to be really, really pointed, have you looked at other industrial applications of the technology that you're building?
Definitely I did. And that's a very good question. These are more stationary, as you said, more than moving parts. And that will be a little bit simpler, not as big challenge as this, because this is moving trucks. That's the first thing. The other thing, that they're already working on that. And there are already companies that they're working on that because it's simpler. It's been there for a while. And there's even more, I guess, more than mining, they produce heat is the metal manufacturing. The manufacturing has the biggest heat produced. For example, any manufacturing which includes, metals, melting and so on, right? So there's a lot of heat in there. So, but there I didn't find the gap in the market or in the research. So here I'm covering a gap which is on the trucks, which is more challenging, and people didn't really succeed as much and did the same as me. That's why I'm covering that gap, not other gaps.
Gotcha. Thank you very much for the presentation.
No problem.
Again, go ahead. Go ahead.
One thing. I guess if I move to the other round, what Mr. Martin said for the electrical system, I think that's a very good comment. I think I should add more into that. I thought it's just electrical generation. I don't need to mention a lot about that, but I think I should add that part to my schematic as well. So thanks for that.
Thanks so much, Yusuf, for your presentation. Really looking forward to circling back with you at a later time. So what I'm going to do now is bring up our next presenter. And just by way of introduction, our next presenter is going to be Colette Pillsworth. And Colette is going to be speaking to us about fracture coatings vectors for mineral exploration. So Colette, the floor is yours. Please go ahead.
Awesome. I'll just share my screen and then get going.
Sure.
So while she's sharing her screen, should I stay or leave?
Oh yeah. Please feel free to stay.
Can you guys see my screen?
We can.
Yes, we can.
Okay, awesome. So hi, everyone. My name is Colette, and I'm currently doing my PhD at Queen's University under the supervision of Daniel Layden Matthews and Matthew Labon. So today I'm going to be giving a lecture on fracture coatings, and I'll be showing how we can use them as a vector for mineral exploration. And this is part of my current PhD research. I hope you find it informative, and I look forward to your questions. So society is facing a challenge in that the next discovery of ore deposits is undercover and at depth previously not explored. This is a challenge as we need new ways of exploring for these deposits. And this simple block model on the screen shows a buried ore deposit within a Canadian environment. And one way in which we can do this is the use of geochemistry. And we use geochemistry as ore deposits are very distinct geochemical anomalies that create a deviation in element concentrations that are different from the geochemical baseline in the area. Ore deposits are also associated with primary dispersion halos, which occur with the original mineralizing system and tend to be limited extent as seen and close to the ore deposit, and secondary, which is associated with a remobilization of elements from the ore or primary alteration zone after ore deposit formation, and tend to result in the secondary dispersion halo as seen on the slide that is much lighter than the primary one. We care about this as the bigger the geochemical footprint of the ore system is, the more chance we have of finding it. And so in exploration, we apply different geochemical techniques and methods to detect this footprint. There is a lot of mechanisms that play a role in moving these elements around the ore systems and creating these dispersion halos. And there's a few that these are just like a few of that have been documented within the VADOS, which is below the water table, and the Favoritic zone, which is below the water table. But the main takeaway I want you to take from this figure is that there is mechanisms that do exist, but fractures are facilitating a lot of that, of these other mechanisms, and it'll be what my talk is on today. So these fractures are important as we provide open permeable pathways in which fluid or potential gases can move elements from mineralization into the surrounding rocks and overburden. If these fluids are associated with an ore deposit formation or have encountered an ore deposit nearby, they could contain like a higher concentration of ore associated elements that are different from the geochemical baseline. And as these fluids pass through fractures, it leaves behind a very distinct mineralogical and geochemical signature on these fracture coatings, which could be useful for exploration. And this video that is just playing is a photogrammetry model, which shows a fracture coating exhibiting a thick red iron oxide coating. It is not the white vein. And I get a lot of questions about what is a fracture coating. And so this red iron oxide stain is what I would be kind of, concentrating on and showing how these fracture coatings can be used in exploration. So why do we care so much about these fracture coatings? I've just said they act as pathways, but have they ever been proven to be useful? So there was a previous study on fracture coatings that was undertaken surrounding the McArthur River unconformity hosted uranium deposit in the Athabasca Basin in Canada. And this study showed that 7 main types of fracture coatings existed surrounding the deposit, and they differed in terms of color, mineralogy, and chemistry. And the 7 main types are just shown here. And overall, this research showed that fracture coatings extend the footprint of the ore system. And if we recall, this is great as it increases the chance of finding an ore deposit, and that the mineralogy and chemistry of the fracture coating can indicate proximity to mineralization. However, there was a bit of a gap in that knowledge, in that research was indicating that fracture coatings are useful for exploration, but research really needs to be applied to other ore deposits in different geological environments, to understand limitations, increase case uses, to overall understand its effectiveness for exploration programs. As not all systems form in the exact same way, and many of the mining companies do discard fracture samples as we don't want to influence their assay data, and we don't really sure how to use them. But studying fracture coatings also in other geological environments is a challenge, as not all fractures have sufficient coatings. So if we were to use the previous method to gain chemical information from fracture coatings, which involves the removal of the coating with a dental drill to produce a powder, and then you react that powder with different acids to gain the information about the chemistry. In samples with a very thin coating, as seen here on the black sample coating on the screen, you'd end up sampling the host rock as well, which is bad because that host rock also would contribute a chemical signature that does not reflect the most recent fluid flow within the fracture pathway. And that actually could dilute the chemical signature that is being recorded on the fracture coating from the dispersion of elements associated with potentially a proximal ore deposit. So the first part of this research, and I'll be talking about today, is how you develop an in situ method for analyzing the chemical composition of these fracture coatings. And the second part of this research is actually applying that method to fracture coatings surrounding the Oberon gold deposit in the Northern Territories of Australia to see if fracture coatings could be used as a vector for mineral exploration in the region. So now I'm just going to talk about how you develop an in situ laser ablation ICP-MF method to analyze element content on fracture surfaces. So laser ablation ICP-MF stands for laser industrially coupled plasma mass spectrometry. This technique requires that you mount your sample in a sample chamber, as demonstrated on the slide, and the surface of your sample is then hit with a focused laser beam, which generates this fine particulate matter. These ablated particles are then transported to a secondary excited source of an ICP-MS instrumentation for digestion and ionization of the sample mass. Once the sample is converted into ions, it is measured using a mass spectrometer. And a reason I kind of wanted to use this technique is it allows for the direct targeting of the fracture surfaces and minimizes the contribution of the host rock to the geochemical signature. You can basically see where you're ablating and then also minimize the effect that the host rock has. So this is just an example of one of those fracture coatings mounted on a thin section slide. And there is a few considerations that we needed to take into account before applying this technique. Most of the time you deal with very flat samples in this sort of system. As you can see, this fracture coating has a lot of topography. It's highly variable. And this kind of meant that traditional line ablation, which is lasering lines across the sample, could not be used. And also you have to consider the thickness of the fracture coating, as it's not uniformed across the sample, which meant we had to consider the amount of time we lasered the sample for. So to analyze these fracture coatings, this is the workflow that has been developed to measure the element content on the fracture coatings. It consists of mounting a section of the fracture coating on a thin section and then producing like a low backscatter electron image. So as you can imagine, a really high magnification microscope to identify and see textures and minerals for analysis. Once you've targeted it and you've located it on the laser system, we can use this cell space grid pattern. And this cell space grid pattern was used to avoid that topography issue that I mentioned earlier. We also reduced the data in ILite4, which is a software package developed for the processing of laser ablation ICP-MS data. We also cut the time of the analysis to 5 seconds, as this was found to increase sensitivity and only analyze the target, the surface area of the sample, representing the most recent fluid flow, accounting for the issue we talked about changing mineralogy with depth. Overall, this produces a rasterized geochemical map and on the allowing you to see the element distributions on the fracture coatings. So this slide shows some of those rasterized geochemical maps with pathfinder elements. So when I say pathfinder elements, I mean elements that are potentially indicating an ore system is nearby. And this is generated in ILite. The first image on the top right is an SEM image highlighting the location of a manganese oxide that was identified on the fracture coating. It kind of looks like a heavily deformed Australia. And so with these maps, we can do like a few things. We can see the spatial relationships of how elements are distributed on the fractures. We can see that the samples are not homogeneous, which does have implications for using other geochemical non-in situ techniques to analyze these coatings. It also allows us to identify, the mineral phases hosting the pathfinder elements, and we can also see pathfinder element association to association. We really want to be looking for those pathfinder associations because those are kind of what are saying that fluid definitely must have come from a nearby ore deposit, which could be used as a vector for exploration. In addition, you can also generate bulk geochemical values of the sample grid, as highlighted here, with the interpolation of the data points. And you can also do it for specific mineralogy, as highlighted at the bottom. So the manganese oxide, I also pulled up some element concentration values for it. All of which can be kind of used to understand this mineral chemistry relationship on the surface of this fracture coating to be used as a guide for exploration. So once we'd established the method, we applied this method to fracture coating surrounding the Oberon gold deposit in the Northern Territories. This slide highlights the location of the site, the outline of the deposit showing, the multiple host rocks in an anticlinal structure and the surface flooding that occurs at this site. This site does have a geochemical anomaly at surface, which makes it an important case study to do a fracture coating analysis. So you can kind of see how the whole system is working to be able to apply that in a bigger, larger exploration context. So before we applied this method I just talked about, we really had to find out if fracture coatings did exist at this site to be able to use them. So in August 2019, me and my supervisor flew to the site for sample collection. And these are just some of the field observations that we noticed. We noticed that 8 major fracture types exist based off color. Color was used as an easy identifiable feature in the field. The mineralogy and variant nature of the samples makes it easy to classify these things in the field. The 8 meat types consisted of orange, purple, white, red, green, black, brown. And there was also this multicolored fracture type, which could have indicated, multiple fluid flow interaction on the fracture coating. To understand if fracture coatings could be used as a vector for mineral exploration in this region, we had to select a subset of 20 open fracture samples with a thin coating layer to satisfy, different criteria. The criteria for sample selection involved, a range of depths, main lithological units that were hosted in the deposit, fracture colors that I had defined, and across multiple drill holes. This criteria was selected as we wanted to rule out any external controls on the chemical composition of the fracture color. And this figure illustrates where those samples came from, the associated host rock, which drill code they came from as well. In addition, before we applied this laser ablation technique, we looked at the primary mineralogy of the 20 fracture samples. These BSE images just show the main mineralogy and textures observed. With each image, you'll notice a little square, and this just shows the fracture color that this mineralogy or texture was observed the most. The primary mineralogy was consisting of chlorites, coolinites, white micas, carbonates, smectites, and iron oxides. But the main mineralogy and texture I want you to take away from this slide is an A, and this image shows botryoidal goethite, which was common in blacks and purples, and to a lesser extent browns. And I'll go into further in detail in the next slide why that's important. So we applied the laser ablation method that I talked about and generated these bulk element content for each fracture coating. And this is where we integrated the data of the whole sample grid to generate one value for each sample. As arsenic, sulfur, and gold were highlighted as anomalous in all surface media at that site, we indicated a deposit at depth. This figure shows that sulfur and arsenic concentrations taken from the fracture coated, plotted with depth, lithology, and fracture color within the drill holes. Gold is not displayed, as even though it does show on the surface of the fracture coatings, as seen in the top right, it is quite spotty in any integration of that data to generate a bulk composition and mask any signature of the gold. We plotted these values by respective fracture color and against whole rock data, which is affecting the chemical composition of the host rocks in that ore deposit, and as seen in the box and whisker plots on the screen. These elements are chosen as the major pathfinder elements for gold, with arsenic at the bottom and the sum of the rest of the pathfinder elements, such as nickel, copper, selenium, moly, silver, antimony, tellurium, and bismuth plotted above. The results show that fractures record anomalous concentration of pathfinder elements above mineralization in comparison to background, with blacks being the most anomalous in concentrations of these pathfinders. We also noticed that iron controlled the coloring of fracture coatings, with browns, purples, and blacks having the highest iron content, while white green had the lowest, highlighted in the box and whisker plot on the left. Tying this all together, we noticed that high iron equaled high pathfinders, and iron plotted against arsenic shows this relationship to the right, the top right. We also noticed that samples at the highest arsenic and iron also showed that botryoidal goethite that I mentioned earlier. Sulfur, despite showing anomalous values, sorry, I forgot about botryoidal goethite. But the sulfur, despite showing the anomalous values, we didn't see any correlation, and this is due to some gypsum that is occurring on most of the fracture coatings, which is contributing a sulfur signature, which is related to that water table fluctuation that we see at this site. Overall, we're kind of concluding that purple, blacks, and brown fracture types are the best fractures to explore the nearby ore systems in this region, and are the most, because they contain the most obvious signatures originating from a nearby ore system, and should be targeting exploration programs in the Tanami region. I'll just leave you with some few key takeaways from this lecture today. The key takeaways from this talk is that fractures are an important tool for exploration, and the laser ablation method shows that this allows us to study fracture coatings in other geological environments and settings. And when applying this method to a case study such as Oberon, it shows that fracture coatings can be used for vectors for mineral exploration in the region. Thank you for listening, and I hope you have lots of questions.
Awesome, Colette. Thank you very much for that presentation. I have had the pleasure of working with a lot of geologists who do a lot of core logging, and and in the capacity of lifting up the core and bringing it to the desk for them to core log it. So that's sort of was my experience there. But the question I've got for you is, look, I think most people know that water sort of goes down, right? So, or fluids go downwards. At least mostly people think this way. So when you talk about fractures being able to tell you what's underneath the ground, can you just explain the science behind, the minerals that are under the ground sort of being recognized in a fracture at a level that's above where the minerals are? How does that work? If you can maybe just explain that.
Yeah, so you're asking why fluids go up, and yeah. So sometimes, because these fracture coatings sometimes also record signatures that are coming down as well. And we can kind of use different isotope analysis to really define that as well. It was something I wasn't really talking about in my slide today, but I guess it goes back to some of those mechanisms I mentioned earlier in the first few slides. I was saying that there is a lot of mechanisms that move elements around in a system, and those are ones that are also bringing elements from, the ore system and then migrating them to like a redox boundary at the top. So I think one that is probably like an easy one to explain is, sometimes certain elements can attach themselves to these bubbles, which then can migrate up through the fracture coatings. If that makes sense. And then there's also different geological environments to consider. Sometimes, glaciation, there is like some compression, and then once the glaciation retreats, there also is, isostatic rebound, which actually causes the water table to actually flow up to the surface, such as what occurred in the Athabasca Basin, which is why that water came from mineralization up to the surface to show those geochemical anomalies. So yeah, it's a tricky question. There is a lot of research that still goes on about it, but that is just some of a very broad sense of why we know they move up and not down at the same time.
No, thank you so much. You answered that question beautifully. So Colette, there are two other judges that are going to ask you one question each. And now I'm going to ask Edward Thomas to ask the next question. Edward, please go ahead.
Thank you, Colette, and thank you for your presentation. So I'm curious, this is perhaps a subjective answer here, but in your view, this fracture mineralization analysis, how does it speak to traditional drill core assay in terms of improving vectoring into ore body deposits? And in particular, I wanted to sort of drill down on this idea of isotopic signature. I would presume that the time window for mineralization along a fracture is substantially different than the other phenomenology. Are you able to discern isotopic differentiation in distributions in those fractures versus what you might get in the rest of the drill core assay? Does that help you do a better job in vectoring towards the ore body than the drill assay alone?
Yeah, so I'm going to just answer this in like two parts. Is that okay? So the site I was at in Oberon, they were finding these spiky anomalies in their assay data. And actually, it was when I looked at the assay data and I saw where the fractures were occurring, it was noticed that the spikes in the assay data are actually occurring because we were also sampling these fracture coatings, which obviously contained an elevated concentration of these pathfinder elements because we were representing, you know, movement from the ore system out into mineralization. So I guess one bit is just even understanding that they exist and knowing that they do affect assay programs is really beneficial for exploration to either avoid or actually just utilize that data, like start measuring it, just to add another tool to your toolbox, if that makes sense. The second one is, can you just repeat the last bit of your question? It was quite, yeah.
Yeah, I guess what naively perhaps occurred to me is, you know, if I'm able to sort of get a representative isotopic distribution within a fracture mineralization, one imagines that it might be markedly different than what I might get from sort of a programmed drill core assay, right? So one imagines that the fracture, the mineral is transported typically by water, we would imagine, right? And one would imagine that if the isotopes are moving quickly, that the distribution of isotopes of whatever mineral you're looking at might be different than what I see in the drill core sample. It might give me some clues, right, with respect to both the direction of mineralization and from where it originally came.
Yeah, and that is true. Yeah. So in the Athabasca, we've done some work on lead isotope ratios and basically looking at those ratios and seeing, you know, so basically a ratio that's below 0.7 indicates that you're close to an ore system, and as a ratio that is above 0.7 is indicating background and that there has been no decay from uranium to lead. So the idea is that as you move further away from the ore system, yeah, that lead isotope ratio does decrease. So then you'll be able to, the geochemical footprint gets narrower as you go in towards the mineralized system. So yeah, it's looking for like that difference and being able to tag it. And in terms of, do you see that in the drill hole data? Not always, because a lot of the drill hole data, it tends to be one analytical technique, you know, and sometimes, you know, it just gives you an assay of like, you know, arsenic, gold, or sulfur in this case. So you're actually missing a lot of detail which could be gained otherwise, you know, using like these other sort of techniques as well, if that makes sense.
Thank you.
Awesome. Thank you very much, Edward, for that question. And thank you, Colette, for your answer. Now I'm going to ask our third judge, who is the chair of our judging committee, Martin Jones, to ask you a question or two. Go ahead, Martin.
Thank you, and yeah, thank you, Colette. So my question, and we'll try and, well, it's double-barreled, so it's somewhere in between one and two questions, I guess. So just thinking about the technique that you really highlighted there for analysing the coating, the laser ablation, inductively coupled plasma, mass spectrometry. I just wanted to see if I could say that without tripping myself up, actually. It's a bit of a mouthful, isn't it? Did you consider any other techniques? And, you know, so why did you down select to this particular one?
So we did do a few techniques in terms of looking at mineralogy, but are pretty limited in terms of what we can use, because I really focused on in situ. That was kind of the whole point of this. Like, you can, you know, take the powder off and analyze it, but as we talked about, that dilutes. So in terms of, you know, chemistry wise, like in situ laser ablation is definitely one of the only techniques like that was potentially possible with this. Like, there is other in situ techniques, but it wasn't really relevant for measuring my sort of, like, it goes into more isotope work, if that makes sense, rather than actual just element concentrations. So yeah, I definitely feel like this is probably one of the better techniques that you could probably play around with. In terms of chemistry, though, there is a lot more techniques that you can apply. You can look at like a shortwave and visible and near infrared spectroscopy, which can kind of, it's like to do with the absorption vibrations of, you know, how minerals respond to light. and you can kind of use that to class. It gives you a spectrum, and then you can use that to classify minerals. But yeah, I'm just trying to think of in terms of chemistry wise, like we're quite limited in being able to do it otherwise. Yeah. So, and there's also the other caveat is that we did this in situ. We can also compare it to non-in situ techniques, and then now actually understand how much sensitivity has gained by that, and be able to say like you can use non-in situ, but there is this caveat behind that could dilute the geochemical data. So even just having those comparison studies is really important as well.
Absolutely. Yeah, brilliant. Thank you very much.
Great. Thank you so much for that presentation, Colette. Colette, what we're going to do now is we're going to move on to our next speaker and ask you to just stay in the room, and we will get back to you shortly. Thank you.
Awesome. Thank you very much.
Awesome. Thank you. Okay. Okay, our next speaker has arrived, and I'm just going to show us. Our next speaker has arrived, and it's going to be Stephen Stocker-Riff. And Stephen is going to be speaking to us today about carbon capture in mine tailings storage facilities, a path to validation. Stephen, the floor is yours. Please go ahead and welcome.
Hey everyone, thanks for having me. Share my screen quickly.
Yeah, please go ahead.
Okay. Can you guys see?
Yeah, we see it.
Okay. Okay.
Stephen, just
wrong one.
Yeah, there you go.
Yeah.
No problem.
One second. You know what? I'm just going to share my other screen.
There you go.
Is that better?
Yeah, you're good.
Okay, sweet. So hello everyone, my name is Stephen Stocker-Riff. I'm a Queen's mining engineering student, and I'm doing my master's in carbon capture with mine waste. So I'll tell you a little bit about my research. So the IPCC is the International Panel for Climate Change, and they kind of do these projections for global warming into the future. So here is the graph, you've probably seen it before, for projections up to 2100. And basically what we can see from these curves is that most of the projections we have right now are anticipating us to not meet our target of 2 degrees maximum warming. And this 2 degrees maximum warming is where we say that the climate's going to be profoundly disrupted. So really, there's kind of a global push towards reducing our emissions. And the implications for climate change and not reducing our emissions are significant loss of coastal land and displacement of communities, decreased food and water security, increased severity and frequency of natural disasters, and loss of biodiversity, among many other issues. And the culprit of climate change and global warming can be carbon dioxide. So carbon dioxide is bad because we have this greenhouse gas effect where greenhouse gases such as carbon dioxide in our atmosphere reflect heat back into our atmosphere when the solar radiation comes from the sun. And so too much CO2 is bad. We're used to having a little bit of CO2, but levels are going up too high, and so we need to mitigate some of these CO2 emissions. And so the efforts to mitigate climate change, governments have made pledges to reduce their emissions. So this is like the Paris Climate Agreement, where lots of countries around the world have pledged to reduce their emissions by 2050 to pre-industrial levels, which we are not on track for. And so governments still are trying to push these incentives using policies so that industries have incentive to reduce their carbon emissions, because otherwise they'll just kind of go along as they have for the past 100 years. And so one example in Canada, which is where I'm from, is the carbon tax or carbon cap and trade system. So what is a carbon cap and trade system? Essentially, everybody gets an allowance. So you're allowed to emit a certain tonnage of CO2 as a company. And if you don't emit your allowance, if you reduce your emissions, then you can sell those in a market to big emitters. And so it creates this marketplace for companies that are low emitters to make an alternative source of revenue. So if I'm a company and I want to reduce my emissions and take advantage of this system, how can I do it? I can either reduce my emissions and mitigate them, or I can capture the CO2 that I'm producing. So mitigation is like if I was a coal power plant, maybe I start producing energy using a solar panel instead, or wind energy. And in my field, in mining, companies are doing this by converting their diesel heavy high emission equipment to electric and hydrogen powered vehicles through the use of renewable energy for electricity. So maybe they power their processing plant using a solar farm or a wind farm. But still, even with these mitigation strategies, some CO2 must be produced. So we can't get away from it in the mining industry. So this has to do with metal extraction. So when you extract the metal, so if you think you have like ore is in the ground in these minerals, and we need to extract say nickel, valuable metals from that ore, and we do that in a smelter. So we melt it down and we separate our metals from the gangue, which is all the other rock that we don't want. And smelting produces carbon dioxide because we use carbon as a reductant. Essentially, we really need to use carbon in smelting because it's really good at separating metals from all this other stuff that we don't want. And you might say, okay, well, let's just stop producing those metals, but we need metals like nickel, cobalt, copper to produce wind turbines and solar panels and all these things that we need in modern society. So we can't mitigate these CO2 emissions. Maybe we can capture them and store them in something permanent, right? Keep them from going into the atmosphere. So CO2 capture and storage, here we have depicted, this is a deep saline aquifer storage. So what you can do is you can pump CO2 emissions down into an aquifer deep below the ground. So this would just be one example of diverting your emissions into another permanent storage spot. So deep saline aquifers are actually really cool, but we don't have deep aquifers that we can pump CO2 into everywhere. So they're very location dependent, and they still do have a relatively high energy cost. They also inject CO2 into natural gas reservoirs and oil and gas recovery, but this is exclusively for oil industry, and we're trying to move away from oil, so kind of counterproductive. And then pre-combustion carbon capture in a solvent, so they have like ammonia solutions that you can use at, say, a power plant where you're producing emissions. But these are really not economical, and all the major projects that I've read about in the literature have kind of not been too successful and at a very small scale. So what I focus on is a fourth option, which is mineral carbonation, which is free. And this is really key because a lot of these processes are very process heavy. You need to build lots of equipment, and they tend to be very expensive and involved, but mineral carbonation is not the case, and I'll show you why. So this is what my thesis topic is. I'll give you guys some background on what mineral carbonation, carbon capture is, how it fits into the mining space, and then my research, which is three major goals, which was understanding reaction kinetics, modeling it at a mine scale so we can understand how much carbon we capture at a mine, and then optimizing carbon capture in a mine scenario. So what is mineral carbonation, this carbon capture storage? I'll call it a technology. It's a chemical reaction. So if you have a mineral that contains magnesium or calcium, and the reason why we want magnesium or calcium is because they have a +2 charge, which means they can hold a CO2 molecule. Basically, so you have magnesium bearing mineral, which reacts with carbon dioxide, and it forms a rock, a mineral. And this happens spontaneously. You don't have to do anything to it. It just happens in nature. So that's really key. We don't have to heat it up or put it under pressure or anything. And so a good example of this is limestone, which you can find in nature all over the place. Limestone is CaCO3 or CaO, calcium oxide with the carbon dioxide molecule. So it's literally holding CO2. And if we broke that limestone up chemically, then we would have more CO2 in the atmosphere. So where can we find, so typically magnesium is better than calcium. So where can we find lots of magnesium bearing minerals that want to soak up CO2? So all the stuff that's on the surface, it's been reacting with CO2 geologically, right? It's been exposed to carbon dioxide for millennia, right? So this is where mining ties in. So when we dig up minerals and process them and extract minerals, we take it out of minerals that are underground, and those haven't reacted with CO2. So that's kind of our opportunity. And so this is a picture of a tailings storage facility here. And I'm just gonna make my pointer a laser. So this is a TSF or a tailings storage facility. And so you can imagine these are huge land masses. And so if this was all reactive mineral that could soak up CO2, that's a big opportunity that we can take advantage of. So what mines are good candidates for this? Because not all mines necessarily have these like reactive magnesium bearing minerals. So they're called ultramafic mines. And ultramafic means high in magnesium and iron, so that's mafic. So these deposits are associated with valuable metals. So that's critical because we need to go exploit these deposits for metals, and then typically carbon capture is a byproduct. So they're associated with nickel, copper, and cobalt metals predominantly. So Mount Keith is the classic example where this was first discovered, where they found that 40,000 tons of CO2 was being sequestered in their TSF by accident. And so this was kind of people just stumbled upon this in the late 90s, early 2000s. And ultramafic mines aren't super common. And as we're depleting sulfide deposits, your traditional mines are being depleted, and we're developing ultramafic mines. It's being more popularized, this mineral carbonation thing. So it's unconventional to have an ultramafic mine operating right now. So I'm working with a Timmins junior mining company, which has an ultramafic deposit, to understand their rates of carbon capture, to model their carbon capture once they build their mine. They haven't built it yet, and then optimize it in their TSF, because no one's really done this before. So the first step I'll take you guys through is understanding rates of carbon capture. So when we understand kind of kinetics of a reaction, we want to think about critical reaction parameters. So what affects our rate of reaction? So we have water saturation of pore space. So if you think of this as tailings, or basically tailings is like sand, we have a certain amount of water and gas in between the little grains of sand. So that affects how fast we react. We have depth, so how far from the surface are we? Temperature, if we're hot, we react faster. If we're cold, we react slower. And then we have progression of the reaction. So this is called passivation. So essentially, this is a shrinking core model. So what that means is you have a little reactive grain. This is a bunch of magnesium. It's ready to go. It wants to react with carbon dioxide. Once it starts reacting, it forms a crust of products. So that's like the limestone or something would be forming on the outside. And that makes it harder to get at this reactive core. And so at a certain point, when you've formed enough of a crust around the outside, you have a totally passivated grain. So that means that no CO2 can get through this little product layer into our little reactive grain, and the reaction stops, even if we might still have some leftover reactive grains in there, right? So essentially the implication of this is as we react over a long period of time, we get slower and slower reaction rates because we get more and more passivated. We get a bigger and bigger crust forming on our particles. So I'm just going to go through trends. I'm not going to really go too in depth into these, but basically as part of my research, I've quantified the effects of all these parameters. So here we have on all these graphs, you'll see a percentage of some maximum rate, so they're baseline, versus our critical reaction parameters, so water saturation. So how does water affect our reaction rate? When it's dry, it doesn't react very fast. When it's too wet, it reacts really slowly. And then we have a kind of a perfect maximum at like a 30% water saturation. We can do the same thing for temperature. So temperature, as we get hotter, we have faster reaction rates. As we're colder, we have much slower reaction rates, and our baseline rate is at 20 degrees Celsius. And then for passivation, we ran kind of a long-term experiment. So how does our reaction rate take place over a long period of time? And so we ran it over 207 days. And the gist of this graph that I want you guys to take away is that we have a plot curve for each centimeter layer. So we broke it down by centimeters. And we saw the pickup in the first centimeter. We had the most amount of pickup, but it slowed down over time. We had significantly less in the second centimeter. And as we went lower and lower, deeper into our tailings, we had close to negligible pickup at depth. So we get two curves from this. We get how does our reaction rate slow down over time, and what is the trend of what is the effect of going deeper into the tailings with our pickup. So that's the first goal, right? So we understand how passivation and depth and water and temperature, how all these things affect our rate of carbon capture. So we have a good empirical understanding of reaction kinetics. And now if we can model what the tailings look like in a mine site, so what conditions are our tailings subject to, then we can predict our carbon capture, because we know at what temperature and at water content, how fast our reaction progresses, right? So this is basically the model structure. We take a kinetic trend, we make a soil model, which tells us, okay, in August, our soil is at 20 degrees Celsius. We put them together and we say, okay, this is how much carbon we sequester. So we take the physical characteristics of our soil, we take some historical weather data, so what weather is it subject to, and then we get an idea of how rainfall and weather and like humidity affects our tailings conditions. So we did this using Timmins historical data, which is where the mine site is located. And this is a fancy graph. Don't get stressed out, but it's dry. It's basically a curve of water content as a function of depth. So over here, we're dry, over here, we're wet. And this is a simulation that's telling us how wet our tailings are from 0 centimeters deep to 1 meter deep from April to November. So all these lines that you're seeing pop up are like a day of a simulation. And the reason it's super spiky at the start is because it's basically completely saturated with the water at the start because we just deposited it. So the gist of this is we understand how much water we have in our tailings over the course of our simulation period. And then we understand how much temperature, what temperature we're at with a similar simulation. So in August, we're hot, we're around 20 degrees Celsius. And then towards the winter, we're getting colder. If we let it go along, okay, we're gonna be moving back down as we get closer to, so it's like October, November. You can see the curves are going leftward. And then we compare this with our kinetic data to look at how much pickup we have. So this would be pickup according to depth. But this is the main plot I want you guys to see, which is our cumulative CO2 sequestered over the course of our simulation from April to November. And what this graph shows is 13,000 cars off the road per year. So that's 60,000 tons of CO2 sequestered and $3 million in carbon credit revenue. So the implications of this model are that we are demonstrating CO2 pickup in a tailings storage facility, and an operating mine would need a validation plan to support this model, but it's kind of a preliminary step. And the final note I want to say is that with this model, where we understand how the conditions in the TSF affect pickup, you can then think about manipulating the conditions in your tailings storage facility to maximize your CO2 sequestration, right? So how can we deposit our tailings smartly so that we maximize our rates of reaction? Or do we want to deposit in thicker layers or thinner layers? So these are all things we're kind of exploring with the model right now, which is the final component of my thesis. So I just want to thank you guys for listening. I hope that was a clear presentation, and if you guys have any questions, feel free to ask.
Right. Thank you so much for that presentation, Stephen. And look, I think tailings are one of the things that give mining a bad rap with the rest of the world, in that people are always sort of, thinking mining is making the environment worse because the tailings keep showing up and they stay there for sometimes forever. And then my question is sort of around that forever piece. Have you looked into other use cases of the tailings that have the carbon sequestered in them, as opposed to just kind of leaving them there for eternity, right?
Mm-hmm.
So again, my question is, have you looked into any other use cases for those tailings that have got the carbon sequestered in them? I know some companies are doing things like Carbon Cure is using, or Carboncrete is using, infusing concrete with carbon dioxide. But maybe if you can just comment on where do you think is sort of the next step with your method of sequestering tailings with carbon in tailings?
Yeah, absolutely. That's a great question. So the mineral carbonation reaction, it's when you have like tailings sequester CO2, there's a cementation reaction. So there's been a bunch of studies that have shown like improved structural properties of the tailings. And so this ties into Carbon Cure, and there are cement companies that are using this to improve their cement because it's the exact same reaction. So I think what the mine that I'm working with is, which is not this would be more of a materials research, whereas I'm more on the chemistry side. But I think there's definitely opportunity for building roads out of your tailings and repurposing it as like a building material, I think, and I know you can use it as an additive. But in general, I think in Canada, at least with our TSF, when you deposit all your tailings, really the mine plans nowadays are really robust so that you look at returning the area back to fully revegetated. So the carbon capture is really acute, right? So it's during the lifespan of the mine. And then the thesis is that when you're done producing, when you're done mining, you revegetate. So I think the story of this carbon capture thing would end when the mine stops producing.
Thank you for that. And Stephen, we do have two other judges that are going to ask you a question or two each. And I'm going to call upon our next judge, Martin Jones, to ask you the next question. Martin, please go ahead.
Thank you, Charles, and thank you, Stephen. So sort of following on a little bit from what Charles was just asking you, I'm interested in if you understand the sort of the size of the opportunity really for this. You mentioned that the ultramafic mines are quite rare, and now it's limited to the lifespan of the mine. So just on a national or even international scale, what's the size of the opportunity for using these tailings to sort of help us with the CO2 challenge that we've got?
For sure. Yeah, so I think there's a group that came out of UBC that does a lot of research in this field. And I know that, so for British Columbia alone, they looked at all the ultramafic mine deposits that may be economical for development. And they could go to, so this would be like an optimistic forecast, I guess, but you could make British Columbia as a province net zero if you took advantage of all the ultramafic deposits sequestering carbon that are economic, right? So if we built all these mines within the next 10 years in British Columbia, there's enough economic deposits or deposits that could potentially be mined in British Columbia to make the whole province net zero. Now on an international scale, I don't know what the opportunity is for carbon sequestration for carbon credits, because a lot of mines look at these opportunities in Canada because we have carbon credits. You don't have carbon credits all around the world. But I think in Canada, it's pretty sizable. So I think it's an interesting component of new mines being built nowadays, because ESG, which is I'm not sure, like when you evaluate a company, the environmental component is becoming more and more important for mines to be developed. And so this is like a really nice way to meet those standards of low carbon metals and stuff like that economically. So I think it'll become more and more prevalent as carbon emissions become more and more of a focus on heavy industry.
Brilliant. Thank you very much, Stephen.
Great. Thank you, Martin, for that question. Next, I'm going to call on Edward Thomas to ask the next question. Edward, please go ahead.
Sure. Hi, Stephen. Thank you for your presentation. Well, let's bring it back to a bit of chemical engineering. You've got a bit of a sense of the kinetics of the sequestration reaction. So it's not a scope question, but it really has to do with the time scope. It seems that if you like, the first few centimeters of overburden are basically carbon saturated fairly quickly. Mm-hmm. So without a commitment to further keep processing the tailings, for what duration is an ultramafic tailings deposit doing the job of sequestering carbon? Is this a 1 year proposition? Is it a 5 year proposition with a bit of overburden processing? What does that look like?
Yeah, great question. So I think it depends on what your goal is, right? So in our project, so the model that I presented today did not incorporate any deposition, right? So if you look at the results that I show here, this is like you deposit a layer of tailings and you let it soak up CO2 for a year. But if you think about it in real TSF, like a mine is continually producing waste, right? So instead of having one layer of tailings laid down and watching it soak up, it's gonna basically you'll always have fresh tailings. So you won't really get the effect of passivation where in reality, because you're just going to be pouring more tailings on top and on top, but you also won't get your maximum conversion of your potential, right? The potential is being lost because you're constantly burying minerals that haven't soaked up all the CO2 that they can, right? So if we could spread these out so thinly that they could react to completion, that would be great, but we would need like the whole province of Ontario to do that. So it's not super realistic, but it's balancing that effect of getting as much carbon capture as we can out of the tailings, but working within the operational constraints of what's feasible at a tailings management perspective, right? This mine is producing 30 to 100,000 tons of tailings a day. That's a lot of tailings, and so you have to work within those constraints.
Have you toyed with the idea of any dispersion technology? I mean, obviously a fluid bed's getting a bit radically expensive, but just sort of a simpler spreading regime.
Yeah, so like a fluidized bed, you mean?
Well, that's rather extreme, but or some other optimizing technology.
Yeah, so you always look at this and you say, okay, if we can't get as much of the carbon captured as we want because we're burying it, why don't we put it in a reactor and heat it up and put it under pressure and let it soak up the CO2 as quickly as possible? Because running these in a process sequesters CO2 way faster, right? But we're working within what's feasible. Like I said, we're producing 30 to 100,000 tons of tailings a day. And so designing equipment that can handle that kind of load is incredibly expensive. And so that's why we look at simple low-cost opportunities, right? So you could think about, should we build an autoclave and put the tailings in there and blast it? Well, you could, but you'll go broke. So instead, we're going to look at a tailings storage facility and think about what are low-cost interventions we can do that have the greatest amount of impact, right? So that's kind of the direction we have taken instead of the process-oriented, equipment-laden approach.
Awesome. Thank you so much, Stephen, for those answers. And again, thank you so much for sharing this method of sequestering the carbon into tailings. We think the mining industry definitely needs solutions like this for sure. All right, what I'm going to do now is call our next speaker. But before I do that, I'm going to just pull up a screen here to share, and then we'll go from there. Here we go. One more second. Sorry about that. Sorry, almost there. Okay, so our next speaker is Kate Fraser, and Kate Fraser is going to be speaking to us about plastics for renewable energy devices. So Kate, please go ahead, the floor is yours.
Hi, thank you. I'll just quickly share my screen and then we'll be good to go. Oops. Can you all see that okay?
Yes, thank you.
Yes, yes, we can.
Great.
Thank you.
Okay, great. Hi, so I'd like to introduce myself. My name is Kate Fraser, and I will be presenting on my research project as part of the Holdcross group at Simon Fraser University, which is plastics for renewable energy applications. Oh, let me go to my screen. There we go. So the world's energy supply relies primarily on oil, coal, and gas. These fuel sources are known as non-renewable fossil fuels as they take millions of years to regenerate. Currently, we're using them at a rate faster than the regeneration time, meaning these finite resources are soon to run out. So we need to find alternative renewable energy sources. In North America alone, our main reliance is upon oil and natural gas, with Canada being a world leader in the usage of oil, as you can see from the dark green area. It's also a world leader in gas usage, the dark red area. Despite fossil fuels being finite, there's also the additional problem of dangerous greenhouse gases they emit when combusted in an engine as a fuel. The greenhouse gases are made of three main gases. You've got carbon dioxide, which is produced in your combustion of fossil fuels. You've got methane, which is produced in your transport of fossil fuels, and your nitrous oxides, which is also in your combustion of fossil fuels. These fossil fuels add to the greenhouse effect. So when the sun irradiates the Earth, some of the heat is trapped within the Earth's atmosphere. But when these greenhouse gases are emitted, the layer that traps the heat is thickened, meaning that more heat is trapped within the Earth's atmosphere, increasing the temperature. This graph shows an increase in Earth's temperature over time. As you can see, we're now at the hottest level ever recorded. This is already having an effect on the climate, with just a few degrees shift causing irreparable damage to the world's ecosystems and climate control. So we urgently need to find an alternative to fossil fuels. So we have some renewable energy options. Often, the most talked about renewable energy sources are solar, which converts energy from the sun into energy we can use in our homes, or wind, where the wind turns the turbine, allowing energy to converted into energy we can use in our homes. However, there are downfalls to these options. We cannot store the energy. Without storage, the energy generated can only be used immediately or it'll go to waste. So what happens when there's too little sun or wind? The excess energy demand must be met using fossil fuels. Or what happens when there's too much sun or wind, when the supply is larger than the demand? The surplus energy goes to waste. This is not an effective long-term replacement for fossil fuels, so we need to keep thinking. Hydrogen can be used as an alternative fossil fuel. As the most abundant element in the universe, there's unlikely to ever be a shortage. It's also the lightest element in the universe, and meaning it has the ability to store large amounts of energy per unit of weight. And maybe most importantly, when it is combusted as a fuel, only water is released, meaning no greenhouse gases are produced. Hydrogen fuel can be used as a bigger part in the hydrogen economy. So we know that these renewable energy sources produce excess energy. When the immediate energy demand is surpassed, the excess energy can be supplied through an electrolyzer. The electrolyzer converts the water into hydrogen fuel. This hydrogen fuel can then be pumped into a fuel cell, which combusts the hydrogen and allows it to power things such as transportation vehicles. Another good thing about hydrogen is it stores this large amount of energy. In 1 kilogram of hydrogen, we have the same amount of energy as 2.8 kilograms of gasoline, meaning we need half the amount of hydrogen as we do gasoline for the same amount of power. So the two main devices developed for the hydrogen economy are the electrolyzer and the fuel cell. These devices, in simplistic terms, are quite simply a plastic sheet sandwiched between two metal pieces. We've used plastics in these devices to replace the traditionally used liquids, as plastics are more efficient and mean there's no possibility of dangerous liquid leakage from these devices, making them more safe. To understand the importance of these devices, we can think of the electrolyzer as the gas station. This is where the hydrogen fuel is created. The fuel cell can be thought of as the engine. It would replace the engine of a car. You'd fuel the car with hydrogen, and the engine would combust it to power the car. The main focus of my research within these devices is the plastics. So I'll delve a little deeper into this topic. So the plastics are what we like to call polymers, or long chains of molecules. We can think of this quite simply as a chain of people holding hands, with each person being a single molecule. One of the first synthetic polymers was developed in 1933, which was polyethylene, and was first used as a single-use plastic bag in 1960. Since then, the single-use plastic took over the world, and in 1997, there was the discovery of the Great Pacific Garbage Patch. This shows that we're just using too much plastic and it's causing irreparable damage to our ecosystems. In 2002, Bangladesh was one of the first places to ban one-use plastics. And in 2022, Canada has agreed to ban manufacture and importation of these single-use plastics. The plastics have a bad reputation and have become a replacement and improvement for traditional materials, which has caused serious damage to the ecosystems. But sometimes plastics are unavoidable, and we need to make them as long-lasting as possible. The specific plastics that are used in electrolyzers and fuel cells are required to transport charged particles, negative ions, between the metal pieces or the anode and the cathode, the positively and negatively charged metals. These plastic sheets look like this, a simple yellow flexible plastic. If we were to look closer, you'd see a mesh of these polymers, the long chain of molecules. These chains of molecules have positively charged units. And if we go back to our chain of people analogy, it would mean that each person is positively charged, and as opposites attract, these positively charged people would pass negatively charged beach balls or particles along the chain. Therefore, plastics are essential for the development of the hydrogen economy. An issue with the development of these plastics is making a material that can withstand the operating conditions of these devices. At high temperatures and highly caustic conditions, few synthetic plastic can survive to be reused upon exposure to these devices. So there are two main requirements for these plastics. They must withstand the harsh operating conditions. If the polymer was to degrade, it would be like the chain of people separating. They can no longer easily pass negatively charged ball along the chain, causing device failure. They also must have efficient charge transfer. They must pass the ball quickly. To do this, you can increase the number of people and have them standing close together. Or in other words, you'd increase the number of positively charged molecules and make these molecules smaller on the polymer chain. However, if we increase the positively charged units too much, the plastics dissolve in water. These are the challenges the chemist needs to overcome to make these materials suitable. So within the Holdcroft group, we focus on making these plastics suitable for these devices. So the first thing is we need to make them withstand harsh operating conditions. We need to protect the weak links. So the plastic polybenzimidazolium is traditionally used within these devices. So within the Holdcroft group, we identified the weak points, the points we need to protect. So if we think about it this way, essentially, we need to put a helmet on these units. We need to protect the weak areas. And to do this, we added carbon chains, which physically prevented any degradation of these weak points. We also look at making efficient charge transfer. So we need to balance the high number of positive charges, so number of molecules or number of people, and water solubility. We can't have the molecules too small, as they'll be water soluble, but we can't have them too large, otherwise they'll be inefficient. And to do this, we created this plastic HMT PMBI. It still has this protection, you can see in red, but the structure is slightly changed, making it a slightly bigger molecule. These polymers have been successfully integrated into devices. Within an electrolyzer, this plastic was able to withstand the harsh operating conditions for over 10 days, and the fuel cell for nearly a week. Although this doesn't sound like a long time, the previous devices were unable to operate for more than 16 hours. The efficiency of the charge transfer for these materials was better than anything seen before. So now we ask, is it good enough? How many cars can be fueled with 10 days of hydrogen? And how far could you drive if an engine only lasted 5 days before a part needed to be replaced? So it's clear there's still improvements that need to be made. We've done this by systematically optimizing these plastics. We shifted from the traditional, but still protected benzimidazole, the benzimidazolium, the HMT PMBI plastic that we've just seen. We then made the structure bigger and changed the repeating unit slightly. So we changed the molecule, and then we changed it again. And now we're focusing on making it smaller, so more efficient. Gone smaller again, but this was too small. This dissolved. So now I'm focusing on making it bigger. This structure still has protection of the weak points. It still has the helmets, and it still has the efficient charge transfer without dissolving in water. So to summarize, we have good plastic materials. We have good polymers for these devices. These polymers are stable and they're efficient. They have the protection of the weak points, and they can rapidly transfer the ions, the negatively charged beach balls, let's say, from the different sides of the metal. We've also been able to show long-lasting devices. I say long-lasting in comparison to what was previously reported. The electrolyzer was 245 hours, and the fuel cell was over 100 hours. But there's always room for improvement. We need to reduce the cost of these devices to compete with gasoline. This way, world leaders and those that make more of the decisions on these kind of infrastructures will take note. So we need to make longer lasting plastics. We need to increase the efficiency of the electrolyzers and the fuel cells, and we need to increase awareness. We need to let everyone know how good these devices can be. And with that, I would like to thank you all for listening, and I would like to thank every member of my group that did the research prior to me, and those that are still undergoing and helping the research as it is currently underway. I'd like to open the floor for questions.
Okay, thank you, Kate. I've definitely learned a lot more about plastics in the presentation than I actually thought was possible to learn about plastics. So what I'm going to do now is just want to inform you that there are 3 judges, and I'm one of the judges. But I'm going to turn over the first question to Martin Johns, and then I'll follow in afterwards. Martin, please go ahead.
Thank you, Charles, and thank you, Kate. Yeah, really interesting. So I guess the burning question I've got, Kate, based on what you've just been going through, is how much further do you think you can push the optimization of these plastics? And as a sort of follow on to that, do we envision it becoming sort of economically viable in the near future?
So the simple answer is yes, absolutely. I do really think it will become economically viable. So the structure the polymer that I showed earlier on in the presentation, the HMT PMBI, that actually helped start up a company here in Vancouver, Ionoma, and they now produce hundreds of kilograms of it and send it all around the world. So in that sense, once you find the right one, you can run with it. But even from the structure that they took to create this business, they're still constantly improving it. I feel like there'll never actually be an end to the improvements you can make. You can always change the chemistry to see how that improves it. And I don't know if we'll ever find a completely stable forever plastic to put into these devices. So in that case, yes, there'll always be room for improvement and optimization.
Okay, thanks, Kate. Sounds like you're going to be busy for quite a long time then.
I think so. I think so.
Thank you.
Thank you, Martin, for that question, and Kate, thank you for your answer. Kate, my question is sort of going to build up on some of the information they provided us about the history of plastics. I know that there is microplastics in the oceans. There's so many plastics that are in the recycling that are being recycled, and some are even in the waste disposal sites. So with all this volume of plastics already on the surface, right? How is what you're doing taking care of that problem of what's already out there? Is there any way you can recycle the plastics that are already out there, bring them back into your system, maybe recreate them in a different way? I'm just not sure how you're connecting with the problem that's already out there with the plastics that are already in the environment.
So the way that I think about it is, rather than reducing the problem, we're not adding to the problem. So we don't want to, this is why, one of the reasons, despite just having a long-lasting device that you don't have to keep changing parts of, is the reason why we want long-lasting, durable plastics that we try to make. Because this way, if we can get a plastic that would last forever, you'd never need to change it within the device. You'd never need to throw it away and add to the problem. We always just want to make it last as long as possible.
Perfect. Thank you for that answer. I'm going to bring on our third judge, Edward Thomas, to ask you a question or two. Edward, please go ahead.
Thank you for your presentation, Kate. Kate, so within the emerging hydrogen economy, we have a lot of options, right, for not only storing, but also conversion of hydrogen. So you're working in a proton exchange membrane, so low temperature fuel cell and electrolyzers. There are anion exchange or solid state anion alkaline fuel cells as well. I mean, where do you think the specific user cases are going to exist that are perfect for PEMs versus the other fuel cell technologies? Where do you think your work is going to have the most impact?
Yeah, so these plastics are actually for anion exchange membrane because they exchange the negatively charged hydroxides. So I think the way the field is shifting is from the proton exchange membrane devices to the anion exchange devices, because there's the potential, I didn't talk about it in my presentation, but there's the potential to exchange from a platinum catalyst to a nickel catalyst. So in the PEM devices, you needed a corrosion resistant material, which is why they had to use platinum. They had pretty much no other choice. Whereas alkaline, we can use cheaper, more abundant metals like nickel. So I see the field shifting more in that direction to reduce cost.
Excellent. And out of curiosity, the class of compounds of polymer blocks that you're using, is there potential within solid state devices, or is this strictly for an electrolyte device?
I could see there being a potential for a solid device, but at the moment we're still flowing kind of low concentration potassium hydroxide through. But I think the field would like to move towards pure water. It's just cleaner and better.
So thank you.
Okay, thank you very much, Kate, for the presentation. What we're going to do now is, Kate, you actually happen to be the last presenter that we have. And what we're going to do now is move into, sorry, let me just remove our spotlights here. There you go. All right. Okay, could you stop sharing your screen as well? Oh, there you go. Perfect. All right. Yeah, what we're going to do now is move into our sort of in-camera session where the judges are going to sort of speak to evaluate the presentations and come back with a winner. So what I'm going to do right now is I'm going to pause the recording, and I'm going to put everyone who is not the judge, I guess the presenters, into the waiting room, and then we'll bring you back into the waiting room in a moment. So I'm going to just pause the recording now and start to put you in the waiting room. And after a few minutes, maybe 15 minutes or so, we'll bring everybody back and we'll be able to announce the winner. So thank you everybody for the presentation. Okay, welcome back, everyone. The judges have met, and we've come to a decision on who is going to be selected as the winner for the Canadian competition. And what I'm going to do now is hand that over to Martin, who's the chair of the judges committee, to deliver the news. Thank you, Martin. Go ahead.
Yeah, thank you, Charles, and thank you again to everybody that's presented today. The reason it took us so long is because you all did such an amazing job. We have had quite a debate back there, so yeah, thank you for that. It's always fun when you make our job difficult. So yeah, thank you very much. So we're going to announce the top two. So in second place, first of all, was Colette. So very well done, Colette. That was a really excellent job. Thank you very much. And in first place, the winner is Kate, who will also obviously win the prize today and then go on to the World Lecture Competition as well later this year. So well done, Kate. Excellent job. Brilliant. Right, so yeah, thank you very much, everyone. I'll hand back over to Charles now, just for some final words.
Okay, thank you for that. Again, you know what, we want to thank everybody who took the time to come to present. You know what, you all have amazing research that you're working on, and if it's okay with you, you know what, I would personally like to follow up with you outside of this competition, because some of your ideas have a lot of momentum within the industries that I'm very aware of, and we'll be more than glad to speak to you about that. And Kate, if you'd like some feedback from us, or any of you would like some feedback on your presentation, please reach out to us, email us, we'll be able to give you some feedback on your presentation. We are going to have this recorded, it's recorded of course, but we're going to have it packaged in a way that we can actually post it as well, so you'll be able to see some of your performance there. And Yeah, so again, I just want to thank everybody for coming online. Thanks to Lenisa and Effie and Max for helping coordinate all this. And also like to thank the judges, Edward Thomas and Martin Jones, for taking the time out of your busy schedules to judge this competition. And I guess we'll leave it at that. Thank you, everybody. And we'd like to now say goodbye. Thank you.
Always a pleasure. Thank you, everyone.
Thank you so much. Excellent work, everyone. Thank you.
Thank you.
Thanks.